Okay, welcome back. So in the first part of this lecture, or in the last lecture, the last video, if you want, we set up the problem. We described an approximation methods to solve Schrödinger equations, and by expanding the solution in a complete orthonormal set. And today, I want to play a game with you, and I want to apply that in a very, very, very simplistic way, without attempting to be rigorous, without attempting to be accurate in any ways. But I'm going to show you how this idea can already sort of pave the way for a long, 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 long sort of can help you solve problems that in principle are extremely hard to look at. So the problem we want to solve today is the so-called double wall problem. Okay? So I have a potential as a function of x. And this potential contains two wells. And we will devise an approximate solution of this problem. And later, we will compare this solution with the exact solution we can get by using the numerical code that I provided you with. So we can see that we can actually get reasonable results. Okay? So to be specific, we consider a problem in which u of x is some kind of a q naught 1 minus x squared. So, you know, it's a quartic function, and if you tweak a little bit with it and you do a little bit of, or if you sort of, you know, one day you would have said you do a study of function to determine the graph of this. But now you can simply plot it with any program you want. You'll discover that there are two minima at -1 and 1, and a single maximum at naught equals 0. Now, of course, this system has an infinite spectrum, because eventually, if I zoom out, this will become like a growing symmetric potential. So if I look at this from above, from far away, this looks like, and the dominant term will be x to the 4th, right? So it will have some infinite spectrum, which is not going to be the same as the harmonic oscillator, because the harmonic oscillator goes as x squared. I don't know what it is. It would be something. However, let's suppose we are only interested in the lowest states of this problem. In particular, you know, we suppose we are interested in the lowest two states of this system. So let's consider, and the idea is that if I find a very good, excuse me, if I find a very good choice of the expansion set, maybe I can get along with just two basis vectors. So only two orthogonal, or as we shall see, nearly orthogonal functions will be good enough to expand my wave functions to get both the ground state, and I put the 0, and the first excited state. So I am saying first the lower pedix refers to the coefficients that I'm expanding, and the upper pedix reminds me that these coefficients are the coefficients for the ground state, and these coefficients are the coefficients for the first excited state. Okay, so the game I want to play with you is to try to guess what a good function would be. Now let's U naught be, the value of the potential in the maximum, while the value of the potential in the minimum is going to be 0. Now, if you expand this function near this minima, you discover that there are two harmonic oscillators. One sitting here and one sitting here. Let's call this U right, because it stands on the right, and U left. Now, clearly, U of x is quite similar to U left of x for x close to negative x naught, and U of x is quite similar to U right when x is close to x naught. However, Ux is very different from either U left and U right when x is near 0. I guess we all agree on that. But based on this observation, I might say, okay, in the ground state, the wave function sort of should be large either here or here, because that's where the potential is smallest when the energy. So that's where usually you find the particle in the regions of low energy, right? And I know the ground states for both of them. Now, unfortunately, I don't have the right expression with me, but let's say psi naught I use a psi naught. I can use, the idea is to use basically just two bases. One is, and let them be the ground state of this harmonic oscillator and the ground state of this harmonic oscillator. So let me call phi left the ground state of the harmonic oscillator. So basically is the solution of the equation negative h bar over 2m second derivative with respect to x plus u left, the harmonic oscillator on the left, psi left, is equal to 1/2 m omega square x minus x plus x naught square. Oh, sorry, what am I saying? I'm saying stupid things. This is the solution, that's a 1/2 h bar omega psi left. So what is omega and what is u left? Well, u left is the Taylor expansion of u near the point negative O. So this is u at negative O, which is 0. So it's 0 plus first derivative of u near negative O, negative x naught, which is 0 because you see this is a minimum point. So also the first derivative of u is 0. So the only terms that survives here is the second derivative of the potential u calculated in minus negative naught, x naught. And then you have x negative negative naught squared. Conversely, u right is 1/2 second derivative of u, this time at x naught, and this time is x minus x naught squared. So from this expression, you can really read off what omega is in both cases. These two coefficients are actually the same because the second derivative here is the same as the second derivative here. And you can match this. So what you can say, let me find some room for writing this. What you can actually say is that u second derivative, say, in x naught is equal to y second derivative in minus x naught, and you set it equal to 1/2 m omega squared. This is a definition for omega, right? Because you can say that basically omega, let's forget about this for a moment, omega is just twice over m, this quantity. And then, of course, you know the corresponding eigenenergy. So what is psi left? Psi left is my Gaussian with this, proper normalization, and the exponent of now sigma x plus x naught square, where this sigma is not any sigma, is the sigma that we calculated by solving for the ground state. So it's a function of h bar, m, and omega. And, if you look back in your notes, you'll be able to trace what this is actually, what this coefficient is, right? Now, everything that we're going to say in this lecture can be you can bring it to the point of getting the number out. But this will take me some time. But basically, at the moment, all I'm saying is that you can get an exact representation of psi L and psi R simply by using the expression for the harmonic oscillator, shifting the center of the harmonic oscillator to -1 and +1, and using the omega that comes from this value. For the second derivative in x naught, maybe we can evaluate it. Second derivative in x naught is going to be, well, let me compute this for a moment. Second derivative is going to be 2x naught x squared minus x1 times 4x squared for x. That's the first derivative. And when you act with a second derivative, you can act on both terms. So I get 4u naught. When I act here, I will get 2x times x. And when I act here, I will get plus 4u naught x squared minus 1. Now, in both cases, when I set x equal to +1 or -1, the second term goes away. And in both cases, I get that the second derivative here, if I've done calculation exactly, should be 8u naught. Yes, 8u naught. So now, knowing this, then you know that omega is going to be twice times 8u naught divided by the mass. That's my omega squared. And therefore, omega is going to be the root of 16, which is 4 root of, I guess, this is the frequency of my harmonic oscillator. So now I've completely determined the properties of this harmonic oscillator that approximate locally the potential here, and the harmonic oscillator approximates locally. And since I know the wave function of the ground state, I also know the corresponding wave functions, given the fact that the coefficient in the exponents in the Gaussian forms are completely given, and you can find them in your notes. Now, I don't want to jump back and forth across the notes. Let's assume you have written them up. If you don't have it with you, go back and rewind the lecture in which we solve for it and fill up these dots. Now, next step, we assume that my wave function for the ground state and the excited states are one coefficient, phi left. Let me call it phi c left plus 1 coefficient from c right. And I'm neglecting all other terms in the expansion because I thought I have such a great intuition that I can stop the expansion here. Now, I want to emphasize something that is conceptually different from the previous lecture. In the previous lecture, the basis of eigenstates was chosen by diagonalizing an appropriate operator. Here, we are not doing this. We are choosing them phenomenologically. We are choosing two Gaussians that locally solve the Schrödinger equation in both wells, right? And we think we are guided by intuition that this is a reasonable thing to be doing. But since there is no guarantee, but if we were to use a real basis that comes from diagonalizing an exact operator, we would be guaranteed that this would be an orthonormal set, and in particular, that phi left, phi right would be exactly 0. However, in this case, phi left and phi right are actually not exactly 0. This inner product, because the two Gaussian have a small overlap. You see? So this is nothing but the integral of phi left star, phi right star. So since there is a region where both are finite, this integral is expected to be different than 0. However, it is expected to be exponentially suppressed when the barrier becomes high, because when it becomes high, the harmonic oscillator are very steep, and the wave function decays exponentially, and so the overlap between two exponential tails will be very small. So this is a model that should become accurate when the barrier is high or when your OT is large. So it becomes, we expect to find this better and better when U naught becomes large. So the idea is that, we close our eyes to this fact that this is not exactly orthogonal. There are ways to keep that into account in a rigorous way and solve this problem rigorously by going to what is called a generalized eigenvalue problem. Let's not do that in this illustrative question. Let's suppose we are interested in a fairly good solution and we do not want to be too rigorous. Okay? Too accurate. But we'll see we go a long way just by doing this. So what is the prescription then? We take the Hamiltonian and we bracketing with all 4 terms. So we have to evaluate phi L, phi L, phi L, phi right. But this is an emission operator, so I can say it's phi high, phi left, well, in general, it's complex conjugate, but this is an emission operator, so and the functions are real, so they are the same value. And then, of course, I have phi right, h, phi right. Now, the good thing is, I almost have all the ingredients without doing any calculation, because you see, this is the Hamiltonian calculated in the vicinity of the left. So these wave functions are concentrated in the vicinity of the negative x naught point, where the potential is very close to the harmonic oscillator potential. So to good approximation, this is like h left. And so to good approximation, this is actually 1/2 h bar omega. For the very same reason, here, this is the Hamiltonian depends on the potential that in the region where the psi r is non-zero, looks very much like the harmonic oscillator. And therefore here, this becomes, this can be solved to be 1/2 h bar omega, where again the omega is the roots of, I guess, u naught over m times 4, something like that. Now, what is missing are the non-diagonal terms. Now, let's look at them. The non-diagonal terms, let's call it h left right, are psi left, h psi right. So if I write them now, it looks like psi left complex conjugate. Now this is a real function, so I can forget. Psi left is a Gaussian, so it's a real function. I can forget about this. And then it's going to be psi 2m, second derivative of this, plus u naught x squared minus 1 squared psi right. Now, both these terms act on the right or on the left, it doesn't change. But the point that I want to make, since these two functions are exponentially suppressed, whenever this function is large, say on the left, this term here will be small. Likewise, whenever this will be large, this will be small. So in principle, you can, easily do this integral on a computer, because you can compute the second derivative of a Gaussian. It's not something, I could use Mathematica to exactly get this number. Let me call it epsilon, because it all amounts to do two one-dimensional integral and summing them together. Maybe I should do that. I leave it to you, and maybe we discuss it on Wednesday, on the next Wednesday, the results. But I think you'll agree what you need to do. You have to put here a Gaussian, normalized Gaussian, of course. So you have to account for the correct normalization of the wave function. Put your sigma x plus x naught squared, where sigma is a number that you know from the nodes. Here you do the same, then you act with the derivative, and you get two terms. One is the integral in dx of phi left, and then you have the second derivative of your Gaussian. On the right. And then the other term is simply the product of psi left, the potential, and psi right, which is again a function of Gaussian and potential. Now, in this lecture, for the sake of interest, I'll not compute this integral, but I simply state that I expect this to be a much smaller numbers than the ones that I evaluated before, because the ones that I evaluated before, the diagonal terms, concern psi L, H psi L, and this was 1/2 H bar omega, right? Large number, no small parameter, because there was no, so it was basically the overlap of a function with itself, and the function was large where itself was large. So this integral is actually a large number, a number of order 1, they say technically. However, the off diagonal, which we called epsilon, I expect the epsilon to be much smaller than 1/2 H bar omega. Okay, so the matrix I need to diagonalize now is the following. One half h bar omega, 1/2 h bar omega, epsilon, epsilon. Now, clearly, let's look at this. Let's look at this problem. In the limit in which epsilon goes completely to 0, then clearly the barrier. So I'm neglecting completely the overlap. It's like saying the barrier goes to infinity. Then I have two eigenvalues that are completely degenerate, and they both are equal to 1/2. So in the limit when epsilon is equal to 0, then E1 and E0 are, the first two eigenvalues are degenerate, and they are both h bar omega half. Now let's look at now the case in which you have a little bit of overlap. Now there are methods to solve problems like this when this is called a perturbation. In principle, you can do that. I'll take a different perspective. I look at the exact eigenvalues. Okay. So if I look at the exact eigenvalues, I have to look at the determinant of my matrix, 1/2 omega minus lambda, epsilon, epsilon, 1/2 h bar omega minus lambda equals 0. This is the secular equation. And let's look for the, so this will produce a polynomial equation, 1/2 h bar omega minus lambda square negative epsilon square equals 0. And let's solve it. I mean, I hate solving equations using by hands. I'm spoiled. I use Mathematica instead of the simple polynomial. Instead of a simple polynomial equation. So actually, the way I do, I'm on the other screen here, you cannot see it, but I'm inserting this equation into Mathematica, getting the solution. Give me one moment. Now, if you solve this equation and solve this very simple eigenvalue problem, you'll discover that there are two eigenvalues. So you have, what happens is that in what before for epsilon equals 0, there were two eigenvalues and they were the same. Now when epsilon becomes different than 0, that's for epsilon not equal to 0, the two eigenvalues become 1/2 h bar omega minus plus epsilon and 1/2 h bar omega minus epsilon. So what you have is a very small splitting of very small splitting of the spectrum from two degenerate eigenvalues to two slightly different eigenvalues. And if you look at the corresponding eigenvectors, this eigenvector here is 1, 1, and this eigenvector here is 1, -1. Remember, these are the coefficients of the expansion. So this means that the ground state will be C normalization, psi left x plus, you see, same sign, psi right of x. And the first excited state is going to be the same thing, but now with the relative minus sign. Now you can work out these coefficients by imposing normalization and discover these. So by only doing this simple exercise, we've come to the conclusion that the solution of this problem the lowest eigenstates are basically two Gaussians, and the first excited state is this one. That's psi 0, and this is psi 1. And the other thing is the first and second eigen, so let me call it a different sign, different symbol this. And the idea is that the ground state and the first excited states level on this energy scale should be very similar, because they differ only by a small amount. Is this actually true? Well, we can find out. We go here and, you know, we can Emacs our, so we go use our code. If I remember well, I should have put here in the definition of potential also the double well. So this was the standard harmonic oscillator. Okay, this is, as you see, a nice double well. So I call M and alpha and beta. So let's say mass equal 1, alpha is equal 1. So this is basically U naught equal 1, not very large. Maybe we can use alpha equal 2 to make the barrier a little bit higher. And beta is equal 1. That's good because the x naught, the minimum of the potential is actually 1. So let's look at it. Okay, so you see, if you look at the typical differences between the first two and the others, it's not so well done. There's not much to say. It's not, doesn't look like the problem we had. So probably there is a mistake. So let's go back here. Maybe we didn't actually, yeah, -6 and 6 probably is good enough. So let's try to make the barrier a little bit larger. Maybe we want more points. Let's say 200 points. Oh, you see, as the barrier grows higher, the assumptions that the two-wave functions do not overlap becomes better and better. And now if you look at here, the ground state and the first excited states are very similar compared to the typical distances between them and the others. It is technically, you say that they decouple. This energy difference becomes so much smaller than the energy difference between everything else. Okay? So let's do it, let's go even further. And let's assume we have an even higher energy barrier. For instance, let's take alpha equals 8. Now they should be very, very similar. Look now. Right, the ground state and the first excited states are really, really close. So let's look at the corresponding eigenstate. Let me remind me eigenvalue. How is the structure of this guy? Okay, fine. New plot. New plot. And I'm plotting eigenvectors using 1 and 2. That's the ground state. It looks like two Gaussian, with a little bit of overlap in the middle, but they look like two Gaussian. That's exactly what we predicted to be, remember, two Gaussians. Now let's look at the first excited state. That's basically, and it looks like the opposite Gaussian, as we predicted, the blue line. So you can see we have, you can be even quantitative by plugging in the numbers and doing the integrals, and then you can really match these numbers with the ones that we calculated numerically. But I think it's convincing enough that by going down and using this idea of expansion, you get a lot of physics, a lot of information about this system. And in one of the first common lectures, we'll discuss how this phenomenon is actually linked to the mysterious concept of quantum tunneling. But this is for the next lecture to see. Bye-bye.